The first isomorphism theorem for groups is a classical result that's very important that kind of characterizes the connection between a homomorphism and factor groups. We're going to prove it today. Let's get started. Before we can go into the proof of the first isomorphism theorem for groups, there are some preliminary concepts that I need to make sure that we're all on board with. The first of that is a homomorphism. A homomorphism, I'm going to use the Greek letter phi here, is just a mapping going from one group to the next, G to H. We usually denote it like this. And there's one special property about this mapping, is that if I take a product of things, so AB, that product gets mapped to the product of the images. What I mean by that is that phi of AB is the same as the phi of A times phi of B. So this gets mapped to whatever element you get when you map A and B over and then multiply. So we can multiply first and then map, or map first and then multiply. So that's what we mean by homomorphism. Now, in a homomorphism, we have a special set called the kernel. The kernel is a subset of my group G, and what's special about this is that everything in the kernel gets mapped down to the identity element in H. So depending on my homomorphism, this could just be one thing that gets mapped over. I always know that the identity of G will get mapped over to the identity of H through a homomorphism, but there could be a bunch of things that get mapped down the identity, and so we group all those together. That set is called the kernel, and actually the kernel is a subgroup in itself. We actually can prove that the kernel is a normal subgroup of G. Now, anytime you have a normal subgroup, we could have something called a factor group. So the idea of a factor group is, again, let me draw this picture. We have G and H mapping over with my homomorphism phi. The factor group is I take that kernel as my normal subgroup. I'm going to partition my group into different boxes. The first one's labeled K, and the others are the cosets of K. Now, since it's a normal subgroup, it doesn't matter if we do left or right cosets, we get the same thing. And now I'm going to treat this as a group itself, where my elements are not the elements are the boxes that I get from the cosets of K. So this is what we mean by the factor group G over K. And then the canonical homomorphism is a special homomorphism that goes from G to G over K, and the way we map that is we take an element and we map it to whatever coset it belongs. So in this case, if phi is a canonical homomorphism, then phi of G is just going to be whatever coset G belongs to, G over K. That's what we mean by the canonical homomorphism. Okay, now that we have these concepts, let's revisit the first isomorphism theorem. So the first isomorphism theorem for groups says, let's let psi be a homomorphism going from G to H with a kernel K, and then we can say that the kernel is a normal subgroup of G. Now we're not going to actually prove this point. From there we can say that let's let phi going from G to G over K be the canonical homomorphism that we just talked about. Then if that's true, then there exists an isomorphism eta that goes from the factor group G over K to psi of G, and we can define psi as eta times phi. What are we saying here? That's a lot of stuff going on. The picture that we drew earlier, I think, is actually very helpful here. So we have G, we have H. I'm mapping over here with psi as my homomorphism. I have a kernel, and so since I have a kernel, I can consider the factor group G over K, something like that. And then what the first homomorphism theorem is saying is that this factor group and whatever I get when I map everything from G over to into H, which we're calling psi of G, the image of that homomorphism, those two things are actually isomorphic. So these things are isomorphic, and that's what we're calling eta. You can find eta by this relationship, that psi, so if I take an element here and I map it over to H somewhere through psi, what that's actually doing is taking that element, mapping it down to its coset, and then applying eta to it, and you'll get the same element. So here we have two things that are isomorphic. Why would we care about that? Well, let me just give you an example. So let's let our group be the integers, and I'm going to map over to Z3, which is just 0, 1, and 2. And the way I'm going to map them over through my homomorphism is that if I plug in a number, it gets mapped to that number mod 3. So in other words, the mapping of 4 goes to 1 because 4 is 1 mod 3. Okay, so if I take my kernel here of everything that gets mapped down to the 0 element through this homomorphism, that kernel is just the subgroup generated by 3. All the multiples of 3 are congruent to 0 mod 3. So there's my kernel, which means I can consider a factor group Z over the cyclic subgroup generated by 3. And so I have the cyclic subgroup generated by 3 as one element. And then I can have its cosets, which is going to be the cyclic subgroup generated by 3 plus 1. So this includes elements 1, 4, and so on, 7, etc. And then I could have the cyclic subgroup generated by 3 plus 2. Any other coset is going to fall into one of these three categories. So now what we're saying in the first isomorphism theorem is that this factor group Z over the cyclic subgroup generated by 3, which is kind of unusual, is actually the same thing as Z3. And the way we're going to define Z3 is whatever you got mapping from an integer over to Z3 by saying mod 3. Another way of doing that is you could say, well, which coset does it fall in? In other words, what remainder does it have when I divide by 3? And then from there, we're going to map to Z3 just by its remainder. So these two things are isomorphic. I hope that makes sense. Now it's time to prove it. First thing we're going to do is we're going to define what we mean by eta. And so remember, eta is going from the factor group G over K over to H, and we're going to define that by, if I plug in the coset G of K, I want to get whatever G was mapped to through psi. Okay, now it's easy to get this stuff turned around, so please keep in mind our picture here. Here's G, here's H, so I'm going from G to H with psi. I'm using the canonical homomorphism to get down to G over K, and then I'm using eta to go from G over K up into to H. And again, we're mapping whatever A gets mapped to over here, psi A, that's what we're mapping the coset AK to that element. And now my claim is that this is the isomorphism that we're looking for. So we need to show a few things. First, we need to show that this mapping actually makes sense, that I just didn't make up something non-existent. So we'll call that well-defined. Then we need to show it's a homomorphism, and since it's an isomorphism, that is a homomorphism that is one-to-one and onto. So I need to show those two things as well. All right, so let's first start with well-defined. All right, to show eta is well-defined, we need to take two cosets are the same, G1K and G2K, and so we're mapping cosets to elements. And so I need to make sure that if I'm mapping two sets are the same, are they going to go to the same element? Because there's potential that these could go to different places, right? Before we do our mapping, we need to keep in mind that since G1K and G2K are the same, G2 is in the box G2K. G2 can then be written as G1 times something from the kernel. So we can say G1K. So now when I apply my eta to G1K, by definition that's the same as G1, that's psi of G1. Psi of G1 is the same as psi of G1 times psi of K, because psi of K was in the kernel, so psi of K is the identity. So multiplying the identity of H times something just stays the same, right? Because psi is a homomorphism, I can bring those together, G1K, which means I now have psi of G2. And we know now that that's the same as eta times G2K. If I start with the same input, I end up with the same output. That makes sense. That's good. We have a function here. So the thing is well defined. All right, so next we need to show that this is actually an isomorphism. And remember, to do that, we need to show that it's a homomorphism, it's onto, and it's one-to-one. So first, to show that it's a homomorphism, let's use eta to map over G1K times G2K. Now, remember the operation of cosets is that that's the same thing as mapping over G1, G2, K. Okay, according to my definition of eta, that goes to psi G1, G2. And then psi is a homomorphism, so I'm allowed to break that up as psi G1 times psi G2. And then I can go back to my eta language. So now I have eta G1K, eta G2K. There it is. Eta is a homomorphism. Okay, we can say clearly eta is onto. Why is that? Because anything in H, so pick the element psi of B. I know exactly where psi of B came from. It came through eta. It came from the coset BK. So we can find anything in the image of our homomorphism psi. We know exactly where the element from our factor group G over K came from to map to that element it's onto. To show one-to-one, we need to let our outputs of eta G1K equal the output of eta G2K, and then we need to show that that means that G1K and G2K are the same thing. Now it feels like we're doing the same thing 3 times maybe with, or at least like the well-defined, but with the well-defined is we started with 2 inputs and showed that they give the same output. This time we show it's one-to-one, we start with 2 outputs and show they came from the same inputs. But if eta G1K equals eta G2K, that means then that psi of G1 equals psi of G2. This implies then that I can multiply both sides of this equation by the inverse element of psi G1, which we know through homomorphisms is the same as psi of G1 inverse. Inverses get mapped to inverses. And now since this is a homomorphism, I can bring this together as psi of G1 inverse G2. Now, why do I care about that? Because when I map G1 inverse G2 over to H, I get the identity element in H. That means then that G1 inverse G2 is in my kernel. So if I have the coset G1 G2K, I get the kernel. And now if I multiply everything in G1 inverse G2K by G1, I end up with the coset G1K. And so there we get G2K equals G1K. It's one-to-one. Eta is an isomorphism. End of proof. Okay, now at first glance you may think, okay, I don't understand it. That's okay. Go back, go through it a little bit at a time, keep wrestling with it. Don't get lost in the symbols. Try to keep track of where you are. I think this picture is vastly important in understanding this proof. The other thing is you might wonder, who cares? So I tried to use the example earlier where we have going from Z to Z3 and using the cyclic subgroup generated by 3 as a factor group. We build a factor group that is isomorphic to Z3. That's something that's familiar to us, but this will work for any context with groups. As long as you get a homomorphism, the homomorphism will then determine a kernel. The kernel will then determine a factor group, and that factor group is actually isomorphic in the collection of images you get from your homomorphism. So it helps us understand what's going on with isomorphisms at a deeper level. Look, if you have any questions on this, I'd be happy to help. I hope this makes sense. Algebra is a great thing to study. Keep working at it, and I'll see you next time. Thanks for watching.